This presentation is going to look at required practical 1, and that is how to make a standard solution and then use it in performing a titration. So let's start by having a look at how we make a standard solution. So the key equipment, you need this volumetric flask with a lid, you need a balance and a weighing boat, a funnel, a teat pipette, a beaker, and a wash bottle with distilled water in it. So that's the key equipment for making your standard solution. And it's good if you can get yourself familiar with the names of those so that you can use the proper scientific names in your answers rather than writing things like flask with long neck. It's much better if you can say the actual names of these bits of kit. So the first step is going to be to weigh out the solid that you need to make your standard solution. It is not sufficient in the exam to just say weigh out however many grams of whatever. You need to be specific in how you weigh that out accurately. So just saying weigh it out is not going to get you enough marks. It's not going to get you all the marks. So in order to say how we do this stepwise, there's a couple of ways you could do it. The way that I'm going to talk about, first of all, we place the weighing boat on the balance. Then you tare the balance, so you set the balance to 0, and then you add the desired amount of solid to the weighing boat. Once you've done that, you then tip the solid into the beaker and then rinse the weighing boat into the beaker. And the reason that you do this is to ensure that all of your solid is transferred, and it's this final bit that highlights the accuracy of this method of doing things, because you're assuming that everything in that weighing boat went into your beaker, so you need to make sure that's the case by rinsing it. You then stir the solution until the solid is fully dissolved. You need to be clear that it's until the solid has fully dissolved. Now at this point here, it doesn't matter how much water is in your beaker. You can add more water to help it dissolve, as long as you don't go near the total solution volume that you're going to have in the end. So if you're making a 250 centimetre cube solution, you need to make sure that you've got much less than that, because otherwise you're going to put in your volumetric flask, it's going to be too much, and you have to start all over again. The amount of water at this stage doesn't matter as long as it's not close to the total volume you're going to have in the end. Once your solid is fully dissolved, you need to pour the solution into the volumetric flask using a funnel, just to make sure you don't spill anything. And you then need to rinse the beaker into the volumetric flask. Again, this is to ensure all of the compound is transferred and you know that all of the solid that you weighed out is now in that volumetric flask. For the same reason, you also need to rinse the stirring rod into the flask, so make sure that absolutely every single bit of that compound is in that volumetric flask. Finally, you need to rinse the funnel into the volumetric flask, again, just to make sure everything is in there. And then you keep adding distilled water until just below that graduation mark. You then add the final few drops of water using a teat pipette. And the reason you do this is to ensure that you don't go over that graduation mark, that line. If you do, you'd have to start all over again. And it's important at this point that you're viewing the meniscus at eye level, and it's the bottom of the meniscus that you want on that graduation mark. Once you've got your water level up to the graduation mark, the bottom of the meniscus on the graduation mark, you need to invert the flask several times to ensure it's mixed thoroughly and the concentration is even throughout the solution. So now we've got our standard solution, we can use it in a titration. So this is using it to work out the concentration of a solution whose concentration we don't know. So during the titration, the standard solution can either go in the burette or it could be in the conical flask. Either way works. You just need to make sure, particularly for the calculations, that you know which was where, so that you're doing the right calculation, because quite often people assume that the conical flask contains the thing you're trying to work out the concentration of, and that's not always the case. So you need to read very, very carefully so you know whether the titer refers to the standard solution or the unknown. First thing is, obviously, we need to fill the burette, but firstly, we need to rinse it with distilled water. The reason we do this is to remove any residue from previous experiments, is to make sure the burette is clean. We then need to rinse it with the solution that we're going to fill it with, and this prevents any leftover water diluting the solution. Obviously, if the solution were diluted, you would need more of it, so your titer would be bigger than the true value. We then fill the burette with a solution. It does not need to be on 0 because you record both the start and the end reading. So you're recording the difference. So you do not need to have it at 0. You just need to have enough in there for your titration. You need to make sure the jet space is full. So that's the bit below the tap that's highlighted on the screen. If you don't fill your jet space, when you start your first titration and you open the tap, that jet space may fill before it starts going into the flask. And then whatever volume was needed to fill the jet space will be added to your titer. So your titer will look bigger and the concentration of the analyte would look higher. However, you need to bear in mind that this would only affect that particular titer. So it should not affect the average because you only include concordant results in your average. So not filling the jet space will affect an individual titer, but it will not affect the average because you shouldn't be including that because it will be different. It won't be concordant. You then need to make sure you remove the funnel before taking any readings from the burette. And the reason for that is that it could drip into the burette during a titration, and that will make the titer look smaller and the concentration of the analyte look lower than the true value. Although again, you should find that it doesn't affect the average titer because it shouldn't be concordant. So once your burette is full, we can then look at using the pipette. So we're going to use this pipette to measure out a set volume into a conical flask. So we rinse the pipette with water and then the solution to be measured in the same way as we did for the burette. So you rinse it with water first to get rid of anything else that might be in there, and then you rinse it with the solution that you are using to make sure that it's not diluted down by any water that's left over. So same reasons for these two rinses as there were for the burette. You then use a pipette with a pipette filler to draw up the desired volume. So the pipette, obviously, usually they're fixed volumes. You can get variable ones, but mostly they're fixed, usually a 25 centimetre cubed. And again, you need to make sure you're looking at the meniscus of that waterline from the bottom and at eye level. So the bottom of the meniscus goes on the mark telling you that you've got your desired volume. You then need to empty the pipette into a conical flask, but you don't push the plunger down to do this. You use the release button on the side, and then at the end, you touch the surface of the solution with the tip of the pipette to get the final drop. The pipette is actually calibrated to leave a very, very tiny drop in the tip. So if you push the plunger down, you'll force out that drop, and your volume is not as accurate as it should be. You then add 2 to 3 drops of indicator to the solution, and this allows a colour change, which indicates the endpoint. You do need to bear in mind that indicators are weak acids, so we only add 2 to 3 drops because if we add more than that, it could make the titer bigger than the true value because that weak acid will be included in the titration. You then place your conical flask underneath the burette on top of a white tile. And the purpose of that white tile is to make your endpoint easier to spot and it will prevent you overshooting, so adding too much, so having too big a titer. Your first titration, you do a rough run to get an approximate idea of the endpoint. So when you're doing your rough run, you'll add the titrant, which is the stuff in the burette, in approximately 1 centimetre cube portions until you get your colour change. Now, because this isn't accurate when you're adding 1 centimetre cube portions, you never ever include your rough run in the average titer. It is not an accurate run. It's just to get you an idea of the end point. So then for subsequent runs, you can add a volume of around about 2 to 3 centimetres cubed less than what you now know to be your required volume. So if your rough run gave you a titer of 15, you might add, say, 12 centimetres cubed in your next run because you know it's not going to change in that volume. And then you start adding more slowly because you now know you're reaching your endpoint. The idea is to try and get your endpoint, your colour change, with 1 drop of that titrant. Whilst you are titrating, you need to swirl the flask to make sure all the reactants are mixed together and that all the reactants react. Also, you may get asked why we use a conical flask and not a beaker, and the reason for that is because you need to swirl, so it will avoid you spilling any solution during the titration, because obviously the conical has a narrower neck. You do need to make sure that you rinse the sides of the flask down periodically to ensure that all of the reactants are in the solution. So because you're swirling, your solution may go up the sides of the flask, and you're just going to rinse that down with water periodically to make sure all of the compound is down in the solution and reacting. This will increase the volume that's in your conical flask. However, it does not affect the titer because it will not change the number of moles of titrant. That's a really key important point asked about quite a lot. So it's fine to rinse down the sides of the flask. It will change your volume, but it will not change the number of moles, which is what you're trying to work out. When you're titrating and reading your burette, you need to make sure that you're reading the burette from the bottom of the meniscus. You also should be taking your readings to 2 decimal places, where the last is either a 0 or a 5. So it's either on the line or halfway between that line and the next line. So if we look at, for example, the reading we've got on the screen here, that reading would be 3.30. It's quite clearly dead on the line of 3.30. You can place a white piece of paper behind the burette, and that can make it easier to see the markings and easier to make sure you're getting an accurate reading of that burette. In terms of results, you need to get 2 concordant titers. And again, must highlight you do not include the rough run. It cannot be classed as a concordant titer. And you only use a concordant results when calculating your average titer. By concordant, we mean the results must be within 0.1 of each other. So for example, 24.30 and 24.40. Okay, so now we've had a look at the methods of making the standard solution and doing the titration, and we've looked at the reasoning behind some of the steps. Let's try some past paper questions. So the next 3 slides contain question 1. So what you're going to need to do is read through the question on this slide, answer A, and then move through the next 2 slides to finish the question. You may need to keep flipping back to this first slide to have the information that you need. Alternatively, you could write down the key information. It's up to you. The next 3 slides have question 1, so work through that, and then when you're ready, if you move to the next slide after that, we'll work through the answers. So this is part 1. Pause and have a go at this bit. Part 2. And part 3. Okay, let's have a look at the answers then. So for part A here, you're being asked why the student used sodium hydroxide for the final rinse of the burette rather than using water. And the reason you should have come up with is that the use of water would dilute the sodium hydroxide or change the concentration. You need either the word dilute or concentration, one of the two, to get this mark. Okay, part B then, this is just completing the table to show the titer. Now, if you read the examiner's report for this question, even though it seems relatively simple, very, very few students, as in around 15%, got the mark for this. And the reason was usually incorrect precision. So the only correct answers are the ones that are on your screen now. The rough run was to 1 decimal place, but each of the accurate titrations, the titer should be worked out to 2 decimal places. If you put 23.9, you would lose that mark. It had to be 23.90 and so on. So all of your titers should be to 2 decimal places. For part C, calculating the mean using the concordant results, you should have got 23.95 for 2 marks. The key thing here was spotting that you only use the concordant results in your average. So you should only have been using results 1 and 3. 2 is not concordant. It is 0.2 away from the next nearest. So run 2 should not have been included, and the rough run absolutely should not have been included. So if you're using 1 and 3, the average is 23.95, and it must be to 2 decimal places. The average should be to 2 decimal places. If you did work out the average of 1, 2, and 3, you'll have got 23.86, and that would have got you 1 of the 2 marks. For part D, the total uncertainty, you should have got 0.63%. So that's just doing the total uncertainty divided by the average titer and then timesing by 100 to make it a percentage. According to the examiner's report for this question, one of the most common mistakes was doubling that uncertainty, so doing 0.3 over 23.95. That's because they've not understood that the 0.15 includes both an error for the start reading, the end reading, and also that 0.05 that we add on for uncertainty in the end point. So the 0.15 was the total error for each time. You did not need to double it. That's already been done. Looking at part E, we're looking to find the mass of citric acid in milligrams. So the calculation you should have got is this, given a final answer of 776 milligrams. And the most common mistake in this, according to the examiner's report, was using the wrong volume for the sodium hydroxide, so using 25 rather than 23.95. And that's where it's important that you figure out which of the solutions is in the burette and which one is in the conical. Because if you've used 25, that means you've assumed that the hydroxide was in the conical, and if you read that question back, it's not, it's in the burette. They did say that the conversion from grams to milligrams was done well, but if you didn't do that, you would lose the last mark. For F then, calculate the percentage purity of this sample. All you do is the 776 from part E divided by the total mass from the question, which was 784, times by 100 to get 97.7%. Now, it does say in the mark scheme that in the examiner's report that only 50% of people got this right and 20% didn't even try. So make sure that you understand how you do this final bit, calculating the percentage purity of the sample. Question 2 is all on this one slide, so pause and have a go at this one. Okay, so for A, the effect that this mistake would have on the value of the first titer, you should have said that the value of the titer would be higher than the true value. So if you've got an air bubble in your jet space, the bit below the tap, that will fill when you open the tap, and whatever volume is needed to fill that bit will be added to your titer, so the value of the titer will look higher. For B, the effect, if any, that this would have on the average titer, it should not have any effect. And the reason is that it would not be a concordant result, so it would not be included in the average. So it should have no effect, will get you 1 mark. And then the second bit is for saying that the first titration would be ignored, or that it wouldn't be included, or subsequent titrations would be accurate, and that first one would be missed out of the average. The examiner's report for this question says that students were kind of referring to the right ideas, but were not saying things clearly. So their expression, their language wasn't very good. So you need to make sure you use mark schemes for this kind of question to get your language appropriate. Question 3 then, this again is all on one slide. So pause and have a go at this one. Okay, part A, a reason for removing the funnel after it's been used for filling the burette. You should be talking about a droplet from the funnel entering the burette, which would affect the volume. Suggest one other source of error in the burette is an air bubble in the jet space. Now, it's important to note that this was the only correct answer, and in the examiner's report, they say that a lot of people talked about operator errors rather than errors that are inherent to the burette. So when you're asked about a source of error in the burette, it needs to be the burette, i.e. the fact that you could have an air bubble in the jet space. So it's not operator errors, reading the burette incorrectly, things like that. It's an error within the burette itself. During the titration, the inside of the conical flask is rinsed with the distilled water. Suggest why rinsing improves the accuracy. And that's because it ensures all the reagents are able to react or mix or come into contact with each other. So rinsing down the sides, anything that's been splashed up the side during the titration will be rinsed back down into the solution. And you're making sure that everything reacts. And finally, explaining why adding this extra water does not change the volume of the EDTA that's required. That's because it does not affect the moles of solution, in the moles of stuff in the solution. You don't change the number of moles, and that's why it doesn't change how much EDTA is required. Now, in the examiner's report, they do say that this question was very, very, very badly answered because students have focused very much on learning methods rather than learning them and knowing why you do each bit. So this is about knowing why you take the steps you do in a method. It's important you know not only what to do, but why you do it. Question 4, this again is also all on one slide, so pause and have a go at this question. Okay, so state why it is important to fill the space below the tap in the burette with solution A before beginning an accurate titration. The reason is that if you don't, the space will fill during the titration, so the volume will be higher than the true value. Now, for this question, you must note that just stating that the titer volume will be affected is insufficient. You need to say that the volume is higher than it would normally be. For B, suggest one reason why a 250 centimetre conical flask is preferred to a beaker. This is because there's less chance of losing liquid when you're swirling. Now, in the mark scheme, it quite clearly says that you have to talk about swirling, and in the examiner's report, they do note that the swirling comment was often absent. Students talked about losing liquid if you use a beaker, but they didn't say that that was because you need to swirl. So that bit about swirling is really important. Then during a titration, a chemist rinsed the inside of the conical flask, explained why the water used for rinsing has no effect on the accuracy, and the reason is that it doesn't change the number of moles of the reagents. For D, suggest one reason why repeating a titration makes the value of the average titer more reliable, and that's because you could have a single titration that is flawed or anomalous, and getting a concordant results will eliminate that problem. Finally, question 5. Okay, it's a bit of a longer one, so you need to read the instructions of how to make up a standard solution that you're given there, and then suggest 3 further instructions that would improve the overall technique. So the exam question itself just wants 3. You could come up with many that you might say to improve the overall technique. So have a really good look through that method and then suggest some ways of improving the technique. Okay, here's the answers. So the first point, so this method of weighing by difference, this is not the way that I've talked about doing the weighing. So that first bullet point there, what you would have said from my method is to wash the solid from its weighing container. So basically rinsing the weighing boat into the beaker. Washing the wet rod into the flask or into the beaker. Washing the beaker into the flask once you've transferred. You could also talk about washing the funnel. Using the tea pipette to mark up on the volumetric flask, so for those last few drops to make sure you're dead on the line. Making sure it's the bottom of the meniscus that's on the graduation mark, or finally you could talk about inverting the flask at the end to ensure an even concentration throughout.